Hi there everyone, you're watching a video about solving a system of inequalities. This video is going to be packed with information, so please you make sure you pause and rewind and rewatch if you need to. You don't rewind on YouTube, but whatever. Also, I'm going to assume you know about solving a system of equations, so this will just assume that, but I will review some stuff about inequalities starting right now. What we know about inequalities, right? If we've got x is greater than or equal to 3, we put a solid dot on 3 and we go up. Same if we have x is greater than -1, so not equal to, we put a empty dot and then go up. And here's the less than versions of that. So that's how we draw quantum inequalities in one dimension. Let's move to 2 dimensions. So let's quickly review how to draw a linear graph. Well, there's our graph y equals x minus 3. We've got -3 as our y-intercept, and our gradient or slope is 1. So you go up 1 across 1, up 1 across 1, up 1 across 1. That's y equals x minus 3. But if we draw them as inequalities, here we've got y is greater than x minus 3 and y is less than x minus 3. You see it can't be equal to y equals x minus 3, so you've got to have a dotted line because it can't be equal to. Because this y is the vertical, right? So if it's greater than, it's above. And if it's less than, it's below. Think of it as the vertical height. So if the vertical height is greater than the line, it's above. If the vertical height is less than the line, it's below. Here, we've got solid lines, so these can be equal to. And here we've got below the line, so it's going to be less than or equal to. It's above the line, it's going to be greater than or equal to. What's our equation? What's our inequality? Well, here our y-intercept is 1. And we go up 2 across 1, up 2 across 1, up 2 across 1. So this is going to be y is less than or equal to 2x plus 1. This one, y is greater than or equal to 2x plus 1. Okay, now that you're set with graphing inequalities, we can solve a system of inequalities. Wait, hold the phone. There are 2 more special cases. This one is y is greater than or equal to 2. Y equals 2 is a horizontal line, so it's above the horizontal line. X equals 3 is a vertical line, so x is less than or equal to 3, it's the left hand. It's left of that vertical line. So now we can look at inequalities. System of inequalities. Now we're going to solve this system. The answer is not going to be one point. The answer is not going to be one line. The answer is going to be a region of the graph. So solving it by graphing is what we need to do. So we graph the first line, y equals -3x plus 4, and graph the second line. Now we'll do our shading. Y is less than -3x plus 4, so we're going to shade under the red line. Y is greater than 2x minus 1, so we're going to shade above the blue line. And this purple section, the section that's shaded twice, that is the answer. So you can talk about this as the vertex. 1, 1 is the vertex, and everything this side of that is the answer or the solution to our system of inequalities. Okay, that's easy enough. What's the point of that? The point of that, it helps us with a lot of optimization problems. Helps us with a thing called linear programming. I'm going to give you 2 examples of that now, and so you can see how you could apply that in different circumstances. Okay, Barry is having a barbecue. He's going to make special hot dogs. He's got some special sausages that go in his hot dogs, and he's got buns that they go on. He wants to feed at least 45 people, or at least have 45 hot dogs. Buns come in packs of 6. They cost $2. Sausages come in packs of 8. They cost $3. And he's got $40 to spend. How many packets of buns and sausages should he buy? First step in solving any problem, work out what your variables are, What do we want to know? We want to know how many buns and how many sausages. Let's say B is the number of bags of buns and S is the number of packets of sausages. Okay, now we can do some stuff. Let's look for some keywords. Keyword here is at least 45 hot dogs. What does that mean? Well, he needs 45 buns and 45 sausages. So he needs 6 times the number of bags of buns, has to be 45, and 8 times the number of packets of sausages has to be 45. Or let's simplify that. B is greater than 45 on 6, which, by the way, is 7.5, and S has to be greater than 45 on 8, which is 5.65. The other key word here is budget of $40. So if he's got $2 per bag and $3 per package, $2 per bag of buns plus $3 per packet of sausages has to be less than or equal to $40. Notice I said the word dollars, dollars, dollars. It's all got to be the same units. This side of the equation might be a multiply or divide, might be a plus or minus. You've got to work it out so that the units on the left-hand side are dollars and the units on the right-hand side are also dollars. Same unit on both sides of the inequality. Now we can graph this. Boom. This blue line here, or purple line actually, is this one. B is greater than or equal to 7.5. You see we're shading on the right of it because that's greater than side. This green line is S is greater than or equal to 45 on 8. And we're shading above the line because it's greater than. So the x-axis here is B and the y-axis here is S. And this orange line is 2B plus 3S equals 40. You can see that if you've got, cover up the 3S, 2B equals 40, so B equals 20. That's your x-intercept or your b-intercept, and this y-intercept or s-intercept is 40 on 3. Okay, so what can Barry do? Well, he can do anything in this little region here. So this little triangle here, we call that the feasible region. What can he do? He can do anything that fits in this triangle. So let's zoom in on that triangle. So basically we have 8, 9, 10, 11, 12 bags on the B axis and 5, 6, 7, 8 on the y-axis, which is the S-axis, the sausages axis. So what can Barry actually do? He can't buy half a bag, he can't buy fractions of a bag, he can't buy fractions of a sausage, fractions of a packet. He can only buy whole numbers, so there are 7 options for him, which are these dots here. So he could buy 8 bags of buns and 8 packets of sausages. That would cost him $40. He could buy 8 bags of buns and 7 packets of sausages, which would be 37, etc., 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 etc. So there are his options. Okay, so he has to look at these options now and decide what he wants to do. He can actually work out some more information too. Let me go to the next slide. So now he's got the costs, which is what he wanted to, which was his constraints here. But now he can also work out how many hot dogs can he actually make. So the cheapest thing he can do is 34, which is this dot here, which will give him 48 hot dogs. The most expensive things he can do are this one and this one, the 40. But he'll have extra sausages if he does this option, and he'll have extra buns if he does this option. Probably the best thing he can do, if he does this option, there's no wastage. The best thing he can do is probably this one, 9 buns and 7 sausages, this one here, because he'll have 2 extra sausages left over. Okay, so this is the idea of linear programming, that where the lines cross over, this shaded in region, the region that's shaded 3 times is the feasible region. It's the possible answers to this question, and it tells you what Barry can do. And then you do a bit more analysis. Hey, now you'll notice that these 2 points are the most expensive, and this point is the cheapest. And you'll notice they're the points that are closest to the corners, closest to the vertices of our triangle. And that's actually a real thing. That's a principle that carries over in all these examples. Your maximums and your minimums are going to be on the vertices of your, whatever your polygon here, whatever your region is here. Okay, so if you want to find out the cheapest and most expensive, they're going to be closest to these vertices. Okay, so that's going to help us with our next example. So we've got a random company, let's call them Samsung. They make phones. They have 2 models, basic and advanced. Well, this factory makes 2 models. And they have to make at least 2,000 phones per shift. How many should they make in order to minimize cost? Well, we can't work that out with knowing the constraints. They have to make between 600 and 1,500 basic models. They have to make between 800 and 17 advanced, because they've got other factories that make them as well. They have sales targets they need to make. So this is the constraints. What do they cost? It costs $55 to make a basic and $95 to make an advanced. So what can we do with all this information? Well, we can make some inequalities and one equation. At least 2,000 phones per shift. So basic plus advanced has to be 2,000. Greater than or equal to 2,000. At least 2,000. Basic has to be between 600 and 1,500. Advanced has to be between 800 and 1,700. Okay, so there are our constraints. And we want to minimize cost. So can we get an equation for cost? Yes, we can. Cost is going to be 55 times the number of basic we make, plus 95 times the number of advanced we make. So this is the formula that we'll have to work out costs when we'll find out what the minimum is. This is how we find our feasible region. You'll notice here cost is a function of both a and b. It's not just y equals f of x anymore. We've got y equals f of b and a. Y equals fba. You might see y equals fxy in a lot of books. That's the way we tend to write it. Okay, so let's do this thing. So there's our inequalities. Here's the graph they make. A plus b is less than or equal to, is greater than or equal to 2,000. That's this blue section. You can tell it goes from 2,000 to 2,000 because if b equals 0, a equals 2,000. If a equals 0, b equals 2,000. B is this red section here, and A is this green section here. Okay, so the place where they all cross over is right here, this feasible region. And we discovered before that the maximums and minimums will occur on these vertices. So let's work out what each of the vertices are. Is that one, that one, that one, that one, that one. So we've got 5 vertices, we've got each of their coordinates. What we can do now is take these coordinates, substitute them into this equation, and you'll get the various costs. Let's do that in a table. Okay, so there's our various costs. See, the most expensive thing to do is make a whole heap of phones. The cheapest thing to do is this one. Now, it's more phones than this one, but the combination of phones is better, gives you a cheaper price. Okay, so my recommendation to this company called Samsung is that they make 1,200 basic and 800 advanced every shift. that will fulfill all the targets, and that will be the cheapest way to do it. Okay, I just gave you a lot of information in a short amount of time, so go back and rewatch anything you need to. Remember, with solving systems of inequalities, draw the graph, look at the vertices, look at the feasible region, and make decisions from there. This is a really powerful tool if you can get a handle on it. So work hard and do some more examples for yourself to see if you can do this. All right, good luck with that. Peace.